Very good. So good afternoon. It's my great pleasure to introduce my PhD student, Thierry Liu, from the Computer Science Department at the University of Illinois Urbana-Champaign. We have been, I'm Clara Marstedt, his advisor, also from Computer Science Department, also director of Cognitive Science Lab, and we have been working together on resilient data collection for oil and gas refineries, and Thierry will present some of the results that we have until now, and also some future work that we are this particular quarter now engaging and plan to do 2018, having some really good discussions with oil and gas industry representatives. So this is really very, very exciting research that we will be also talking about.
Thank you, Clara. Hi, everyone. My name is Tian Yuan. Today I will be presenting our work on resilient data collection. Resilient data collection of wireless sensor network in oil and gas refineries. So, in recent years, wireless sensing technology has been shown to have great potential in improving the refinery operation. Back in 2016, Emerson Process Management published a study on how to use the wireless sensing technology to improve the refinery operation. And they suggest that by deploying the wireless sensing technology, a WirelessHART-based sensing technology, they can achieve a saving of $12.3 million per year on typical refinery. And these monitoring technologies, including the heat exchanger, cooling tower, and so on and so forth. And in contrast of the high savings, the implementation cost is relatively low. It only takes around $6 million for the implementation, so that the return of the investment will be only 5 months. However, deploying such kind of wireless sensors in the refineries introduces more challenges. Since these sensors are deployed in open areas in refineries, they are more subject to the cyber attacks. For example, the attacker may have physical access to these sensors, and also they are vulnerable to the hazardous environment. Recent news reports show that Hurricane Harvey destroyed the nation's largest refinery in Houston in August, and also previous examples also show that there's potential when, for example, fire accidents happen in refineries. Such kind of monitoring sensors also went down so that they failed to send the alert, and in the end, it leads to larger scale of the disaster. So these examples all motivate more reliable wireless sensing technologies in the refinery field. Ideally, we desire fast failure detection so that the control center can react faster to these disasters. And also, we want large-scale failure tolerance so that we can tolerate the damage at a larger portion of the sensor network. And also, we want fast and efficient failure recovery after the disaster. And in addition, we want to minimize the risk of the cyber attacks we introduced before. As we are working in the networking aspect, we define the resiliency in the sensor network as the ability for the sensor network to maintain connectivity to the control center under such kind of large-scale failures. The reason we use this definition is that it's very often that in the wireless sensor network, there are a lot of relays and leaf nodes, which are the leaf nodes are basically the sensors. When some relays are damaged, the connection to the leaf nodes also gets lost to the control center. So our goal is to maintain the maximum connectivity to the healthy sensors, given the case that some relays may be damaged. That's how we approach the resiliency issue in the wireless sensor network. Before I introduce our approach, I will spend like 5 minutes to introduce some related technology, which is a very well-known protocol, WirelessHART protocol. It is a wireless mesh network communication protocol for process automation applications. And it is designed based on HART protocol, which was originally designed for wired devices. The failure tolerating strategy adopted by the WirelessHART protocol is done through disjoint multi-path structure. As we show an example here for a two disjoint multi-path between node A and H. Imagine that node A is a sensor node and H is a gateway. This disjoint multi-path structure ensures that no matter which single failure of the relay in this graph, there is still at least one available path between the sensor node and the gateway. In WirelessHART, they specifically deploy two disjoint multi-path structure for every sensing node, which means that for each of the sensing nodes, it has at least two disjoint paths to a gateway, so that it can tolerate single point of failure. However, in the case of large-scale failure, imagine that if we have two failures, for example, C and F here, it's going to disconnect the sensing node from the gateway. So this structure is not very good at dealing with large-scale failures. As we will show in the later slides with some statistics in our experiments, this strategy can only deal with a small portion of the large-scale failure. And in addition, the WirelessHART also implements some security defenses for a large set of different attacks. It includes jamming, eavesdropping, replay attacks, man-in-the-middle, and SIBO attacks. And a key mechanism to achieve the security defense is done by using a join key to authenticate devices to the gateway. So basically, the administrator will configure this join key for all the sensing devices and authenticate them to the gateway so that, for example, the attackers cannot impersonate a communication node as a SIBO node. However, since this join key is shared among all the devices, if an attacker, as we mentioned before, in the refinery, since these sensors are deployed in the open area that attackers may have physical access to them, if an attacker can compromise one of these devices, he may have access to this key, and so that all these attacks may be launched. So having these two major drawbacks of WirelessHART in mind, we introduced our approach to achieve the resiliency of the wireless sensor network. Our approach embeds the resiliency into the data collection framework because by building our defense on top of the data collection framework, we can minimize the extra messages or communication tools we need to implement. And our approach adopts the wireless mesh network for the sensors, and we use multi-tree structure for the data collection path. In order to tolerate large-scale failure, we designed a distributed self-healing protocol in comparison to the disjoint multi-path structure. And our approach reduces the risk of leaking a shared join key by balancing the number of nodes on each of the trees sharing the same key, so that the probability of leaking a key for a tree is minimized. From a higher level of view, our solution can be split into two steps. In the first step, we construct the optimal data collection path for the given topology of the sensor node. And after the deployment of the communication, the data collection path, each node will run a failure detection and self-healing algorithm to recover from failures. Now we're going to introduce the assumptions and the scenario of our model. So we are considering a communication model where the sensor is sending data to a master node via SCADA-like protocol, which means that the master first sends, for example, SCADA read commands to all these sensors, and then these sensors report back the sensing data to the master node. We assume that the sensors all have short-range communication capability, wireless communication capability, and they can communicate within a short range with a bunch of neighboring nodes. And a small set of them are equipped with long-range capabilities, which we can consider them as the gateways. So in this structure, all these sensing nodes will communicate with the master node with a hop-by-hop manner. These sensor nodes will first send the reporting data to the gateway, and after the aggregation at the gateway, it's going to send the aggregated data back to the control center. We use a fail-stop model for the failure, so that this means that when a node fails, it does not come back in a short period of time. This is common in the case that accidents happen. So in the first step, our goal is to construct an optimal data collection path. We first map the 3D topology of the sensor deployment into a 2D graph. We use this simple example to show the mapping, and the blue nodes here represent all the sensor nodes, and green nodes are the gateways. The blue lines, the blue solid lines represent for the short-range communication connectivity, and the double solid line represents for the data collection path constructed by our algorithm. So in this stage, we have two optimization goals. The first goal is to minimize the data collection time. This is represented by the tree height for the data collection path. And a second goal in this stage is that we can any questions? Okay. And the second goal we have is to bound the key leakage probability for the join key we mentioned before. This leakage probability is modeled by the tree size. As we mentioned before, the more nodes sharing the same key will increase the risk of leaking the key. So that by balancing the number of nodes on different trees, we can bound the leakage probability. After the deployment of the data collection path, every node runs a failure detection algorithm for its parent. In our structure, since we do not have the multi-path structure, so every node only has one one parent in the tree, so that the detection, the failure detection can scale. And upon detecting that the parent failed, the node triggers the self-healing protocol by communicating with its neighbors to find out a secondary path to a gateway. For example, if fire happens at several nodes here, which are the relays for these three yellow nodes, these three nodes will be disconnected from their original gateway. And at this point, they will contact the neighbor nodes. For example, for this yellow node we show here, it's going to contact the two blue neighbors and then try to find out a secondary possible path to another gateway. As a result of the self-healing, ideally the connectivity can be recovered so that all the healthy nodes will have at least one available path to a gateway. So we highlight some, we make some highlights on the solutions we have here. In the first stage, we use a centralized planning tool to compute the optimal data collection tree. We model the data collection time optimization problem using the mixed integer linear programming, and use an open source tool, a Groby solver, to solve this optimization problem. And for the leakage, to model the key leakage probability of the shared key, we combine the leakage probability of each node within the same tree to compute the leakage probability, the accumulated leakage probability of a key for that specific tree. And for every data collection tree, we use a threshold to bound the leakage probability so that we can ensure that the leakage probability for every tree, data collection tree, is bounded. In the second stage of the failure recovery stage, we designed a distributed self-healing protocol, and we use heuristic approaches to reconstruct these backward paths, given that the data collection time after the construction is minimized, and also the key leakage probability is still bounded. In terms of experiments, we launched two sets of experiments. The first is based on simulation. We generated a few sets of topologies, the refinery sensor topologies, with up to 500 sensor nodes. And we inject large-scale failure with 2% of node scale. And specifically, to cope with the feature of the locality of these failures, our failure pattern uses a clustered failure so that these nodes, the failed nodes, are clustered together. This is the goal of the locality is to simulate the accident happens, like, for example, like a fire when it starts, and starts, in fact, a small portion of nearby nodes. And in the simulation, we use two metrics, the success rate for recovery and data collection time to measure the reliability and efficiency for the data collection framework. And in a second set of experiments, we implement a test bed with a prototype on Raspberry Pi 3. We use this implementation to evaluate the computational overhead as well as the end-to-end delay for the self-healing protocols. And as a result, we find that our solution consumes only no more than 2% of the CPU utilization, CPU cycles on Raspberry Pi 3, and also the end-to-end delay for recover the connectivity is less than 5 seconds. Now we show some simulation results and the comparison to the WirelessHART technology. So in the first table, we showed that we compared the recovery success rate between the self-healing strategy and the strategy deployed by WirelessHART. The recovery success rate means that the likelihood of recovering from the large-scale failure such that all the healthy nodes will pass to the gateway. So as a result, we can see that the self-healing strategy can achieve more than 90% of the recovery success rate. However, for the WirelessHART, the recovery rate is only more than 30%. And in the second simulation, we evaluate the data collection time before and after the self-healing protocol. This is to evaluate the overhead of the data collection time introduced by the recovered structure for the network. We can see that the red bar here represents the data collection time after the network recovery under large-scale failure. And the green and blue line shows that the optimal data collection time computed before the failure. So as a result, we conclude that the data collection time only increases about less than 7% after the recovery, which means the recovery does not introduce a lot of overhead to the data collection efficiency. In the past year, as we are closing off, we are kind of finishing off this stage of the research. In the past year, we published two papers, a paper at workshop and a technical report. And also, we published two software, a planning tool which takes the topology of the sensor, of the wireless sensors and computes the optimal data collection path, and also an extendable testbed to evaluate the computational overhead and end-to-end delay for the self-healing protocols. In the future, as we've shown in this presentation, our scope and interest is in designing resiliency protocols for oil and gas infrastructures. And in 2018, we will focus on more general monitoring technologies. And currently, we are looking at location-based services, for example, by using drones in these monitoring systems. So that's basically it. If you have any questions, now it's your time.
So when you design your topology, if you're looking at sensors on a pipe, in a sense, the nearest neighbor is determined by the linear topology, the topology of the pipe itself. Mm-hmm. So how does your map of the communication topology reflect the physical topology of the pipes?
Okay, that's a good question. So since we assume that every node only has a short range of communication, so it won't be able to communicate with some nodes very far away. But since so often you can imagine that if you only have one single line of pipe, it's going to be like a node has only a couple of failures on the same pipe. However, a very interesting feature for the pipes in the refinery is that sometimes they are kind of more complex than the straight line, so that there might be some chances that the nodes on one pipeline can communicate with some other nodes on the other line. This will increase the chance that we may use other relay nodes on other pipelines to communicate with the gateway.
So is the communication topology discovered when you start up, or is it part of your map?
In this work, we currently only consider that all these neighbors are pre-computed, so we won't need the discovery protocol for that.
So for the simulation, how long will it take to run the ILP for the 500 sensors?
So for 500 nodes, it takes about 5–10 minutes. It doesn't take a very long time because we did some pruning so to reduce the search space. Some techniques we use here is by, for example, we only consider a subset of the shortest path. So we do not consider the whole searching space in this scenario. Otherwise, you won't be able to deal with for example, 500 nodes.
So the idea is that you will do this once at the planning time, and then that will be that. You compute your trees, and then it will be planned out. But there is no mobility of sensors here.
No, we do not assume mobility.
Okay.
As we heard from the industry, I don't know if you remember Mr. Rivera at the summer school from oil and gas, and we actually had a very good discussion with him just this week on some of these aspects. Refineries and pipelines, it's a long planning process, right? They very carefully consider where they put what. So physical mobility is not part of their equation. And also with respect to the pruning, the physical pipeline infrastructure very much drives the placement of the sensors, right? And therefore also of the communication. So for example, if you have certain pipes and you put the sensor, you physically mount them, right? And if they are too far away, you can immediately basically say, okay, that particular graph connections edge is not going to be part of that, right? So that actually also limits number, but it's not a partial connected ground. Then you can start to work multiple optimal trees. So really nice type of physical system.
So what's the size of a refinery? Is it if you're looking at like hundreds of meters or?
I believe in our simulation we use like 100-meter square box. So, but since we do not, we didn't get any like, we've been talking to these industry people a couple of times, but they are kind of conservative to share with us the specifics about these parameters. So that's our best guess.
And then I think to follow up on the point that Professor Narstead raised, that these are three-dimensional structures.
Yes.
So that you could have a sensor on an inflow pipe that just happens to be, because of the way it's built, close to a sensor on an outflow pipe from a different process. But you can use that in your communication, even though they're somewhat not and not that closely related as far as the process of the pipe, but they're just physically close in space.
Yes, that's true.
That was actually one of the difficulties for the oil and gas refineries to get really a better understanding of discrimination of the various sensors, right? And these pipes. What kind of, I mean, some of the pipes are pushing chemicals, some of them are refined products, some of them are pushing crude, products, and so on. And really understanding much more details of the discrimination of this particular tree should really look at where the raw material is being shipped versus where the refined product one is being shipped, refined product two. I mean, that actually was flowing actually through all of the pipes. We could not get any information, and that actually could be another dimension for this work and self-healing, right? That if one would get our current optimization problem does not take into account that kind of discrimination of trees, what kind of physical product is flowing through that particular pipeline, and how important they are. And there is a fire, right? The fire is actually very much driven by outside, right? It doesn't discriminate that it's currently damaging the raw oil coming in or the refined product going out, right? So we had a really hard time, particularly with respect to sensors, getting more details about the physical environment so that we can actually much more precisely model the cyber part.
But from the communication standpoint, the fact that you've got a sensor on a refined product pipeline, and it just might opportunistically be close to a sensor on the cooling tower, which isn't entirely, process-wise, not that closely related, but opportunistically that can be part of your communication.
Right, and if somehow this is currently what's currently closest, so the tree can be actually built in the communication cyberspace across very precise physical processes. And we currently don't know if this would be the correct approach to model the cyber versus how do the physical...
Makes sense to me.
Yeah, makes sense to us from the cyber part, right? It was so interesting how the refineries are planning their cyber physical system.
So I didn't get this, maybe you mentioned it, but are trees edge disjoint? Are they required to be edge disjoint? Are the connection trees?
In our structure, we don't require the edges to be disjoint.
So the trees can overlap. So the routing trees.
Oh, in that sense, we require them to be disjoint. Yeah. So these trees do not overlap with each other. Because in our multi-tree structure, we only build one path between each sensor node to a gateway. In case of failure of the relay nodes, the path discovery is taken by the self-healing protocol.
So when a node discovers that it has failed, the self-healing, you said it takes about 5 minutes for it to be reconnected back?
Yeah.
And then do you currently impose any requirements on where that reconnection could occur, or it can just not do anything that it finds?
Pardon?
So when it's reconnecting, are there any constraints on which tree it can reconnect with? Or
so the constraint, the only one constraint in this work we mentioned is the security of the tree size of the sharing of the joint key. So if a tree has too many nodes sharing the same key, it's going to deny the discover process.
So nodes discovering nodes around, maybe there are multiple tree nodes, but then the leakage bound is an important criteria and threshold if I can join the tree.
Yeah, just some suggestions for future work. Like my master's thesis, and I sent that to the earlier, is very related.
Yeah, I saw that.
Yeah, I just sent it to you today. So, so in that work, we were really looking at the measurements themselves. You know, so as opposed to a phase job model, we were looking at how the measurements are correlated between sensors. I'm just saying that in your future work, you could consider the fact that, you know, if a sensor has if let's say one link has failed because the sensor has died, maybe a nearby sensor can still alert you to a problem that others would have found out because there's a relationship between the readings that they capture. And so maybe moving forward, you could think about how, you know, if you've got an active route, maybe there's not just a failure and disconnection problem, but you could also leverage relationships between the measurements that these sensors are taking in order to make an estimate for what, you know, another sensor would have said if it was still connected. So you can look at that.
So that's robustness using the physical architecture rather than just the cyber overlay of communications.
Yes, you can leveraging physical relationships. So, yeah.
Ken, one of the things that you mentioned, you cited Emerson's cost savings study. Have you looked at the design engineering guidelines that Emerson and others recommend for deployment of these? Because they build in resiliency to the architecture when they deploy these.
I didn't, well, they mentioned that their solution is based on WirelessHART, but I didn't look into great detail what are the actual resiliency solutions.
Yeah, so there's a public document that's available. I can send you a link to it, called WirelessHART Engineering Process or something like that. Emerson has one, and there's a couple others. They talk about the architecture and how they do the overlays. To give you an idea of size, a refinery, it's typically the number of sensors are I/O points, and so all you need to know is the number of I/O points that a refinery has.
Okay.
So a small refinery would have between 700 and 1,000 I/O points. Some portion would be wired, some portion would be wireless, considering a hybrid install. You're advocating for full wireless. So if you're looking at full wireless, 700 to 1,000 wireless entities. If you have a hybrid, then you have reliability links on the wired side that are different than your reliability links on the wireless side. So you can reason about that combination too. Critical sensors from the engineering principle must be wired. And critical sensors are wired HART installations are explosion-proof enclosures. So wired, like you could have, something can blow up and the wired sensor is still working.
Yeah.
Wireless is not hardened to that same way, but those type of parameters come into play from a physical deployment aspect, not just can I do path reaching from point A to point B in WirelessHART, but what can I rely on and what I can't rely on to provide that resiliency. So you could just say, well, put repeaters everywhere, and now you have lots of pops, and now you can create a mesh. The reality is these sensors are often dense RF space, so there's a whole bunch of them in a place, and that comes into the engineering, which is why they must use wired in some cases and wireless in others, because too many wireless sensors in the same spot, and they exhaust the RF space, they can't talk.
Okay. Thank you for the suggestion.
Right. Any questions online?
So I'm still wondering, maybe you mentioned this, but why do shared keys exist? Why do the sensors have the same key?
This is designed by the WirelessHART protocol. they use a shared key to authenticate the devices to the gateway.
But is there a reason why they can't have their individual?
I'm not sure of what's the reason they make this design decision, but well, at the point we look at the protocol, it's already there.
It's simple, right? I think, and you can predefine it, right? Every sensor you install just gets a key, and they know how to communicate, right? If you would do any other sort of public-private key, you have to have memory and these sensors are simple, right? They don't have very much cyber components, right? We would have to sort of keep the RSA key, then maybe exchange to get sort of to get to RSA, so there's the shared key, and then use shared keys and then change them and so on. A lot of complexity.
Yeah,
a lot of energy.
Clara is common because this key is, as I remember, it's used by the administrator when configuring these devices. They need this kind of like a password to log into the gateway. So that's probably why, because you have too many devices to set up, and you don't want to remember that many passwords for each of them.
That was actually a very interesting case when we worked with some of the power utilities that they were saying that when they installed some of these measurement devices, some of them don't even have it encrypted. It's all plain text, right? And so here at least they have some encryption, some sort of key that they use to send the traffic to their gateway collection.
So they share a key, but do they have a separate identifier, or is that also, like, how do you identify an individual node in the tree? If they share, because it's like a group identification, or you identify each node separately?
Actually, I don't remember the detail of the authentication, but I can check that in the protocol.
Because that opens up a lot of attacks, like if you.
Yeah, sure, definitely.
Yeah, that's what the WirelessHART cards would have, right? So the shared key, and I would say that it's a group key.
WirelessHART has several known vulnerabilities to it.
Yeah, vulnerabilities, yeah.
And it's a TDMA architecture as well.
Okay, once more, questions out in remote land. Once? Twice? All right, let's thank the speaker.
I will give this back to